Hey Chemistry, Mrs. KJ here, going over 3.03 Trends within the periodic table. So the periodic table clarifies trends of atomic size, the size of the ions, electronegativity, and ionization energy. So along with telling the number of valence electrons, whether something is a metal, nonmetal, or metalloid, or being even more specific, whether it's an alkali metal or alkali earth metal. The periodic table also tells us some overall patterns. Trends within the periodic table can be used to predict element properties. In this lesson, you will learn about some of the trends that can be deduced from the periodic table. Trends concerning atomic size, ion size, electronegativity, and ionization energy can all be found and are based on the position of an element on the periodic table. Goals for this lesson: analyze trends for relative sizes of ions and atoms in the periodic table, analyze trends in ionization energy for elements in the periodic table, analyze trends in electronegativity values for elements in the periodic table. You can get your study guide. The periodic table can yield a lot of information about the elements. The periodic table provides substantial information about the elements. Generally speaking, the metals are located in one part of the table, the nonmetals in another, and the metalloids in yet another location. You can determine many other properties of individual elements by knowing about certain trends and characteristics of elements in the periodic table. Examine the periodic table and interpret the block colors, groupings of block colors, and other groupings. For any given element, you can determine many characteristics just from its location on the table. In other words, if I look at nitrogen, at room temperature, is it solid, liquid, or gas? Because it was written in red, I know that it's a gas. Is it a metal or nonmetal or metalloid? I know that is a nonmetal. Atoms vary in size. How big is an atom? As you might expect, atoms are very small, but did you know that the sizes of atoms vary? So not all atoms are the same size. So let's look at this. Fluorine is one of the smallest atoms, while cesium has one of the largest atomic radii. So fluorine is only 50 pms, or picometers, whereas cesium is 260 picometers. So what, 5 times bigger? Even though they're both crazy small, cesium is 5 times bigger than a fluorine atom. Atomic size is a characteristic of an element's atom that can be inferred using the periodic table. It's not possible to measure the width of an atom directly because the location of electrons are not fixed. To solve this problem, an alternative method is used to measure the radii. Scientists use the distance between two nuclei of two identical atoms in a molecule as the diameter and take half of this distance to obtain what is called the atomic radius. This value is equal to half the distance between the nuclei of two identical atoms. So they have to put two fluorines next to each other, and then they can measure how far apart the protons from this fluorine are from the protons of the adjacent fluorine, and then they can divide that by 2, and they can figure out the radius that way. And the reason is because the electrons are always moving. It's not like you can take a picture and say, oh, the electron's right here. I can just measure it directly, so they have to measure it indirectly. How small is an atom really? The distance between nuclei is very small, so small that it is usually measured in picometers, which is 10 to the negative 12th meters. So 0 point and then 11 zeros and then the 5. 1 picometer is 1 trillionth of a meter. Fluorine is one of the smallest atoms again, cesium, one of the largest. So main idea, even though they find the measurements indirectly, the size of atoms do vary. You can use the periodic table to predict and compare atomic radii. Generally speaking, the radius of one atom of an element increases from top to bottom within a group of the periodic table. That is to say, the atomic radius increases with increasing atomic number within a group. For example, when you look at group 2A, you can predict that calcium has a larger atomic radius than magnesium, which is in turn larger than beryllium. So, if we look at this, hydrogen's small, lithium's bigger, sodium's bigger still, potassium's even bigger. So as we go down, the size of the atom's radius gets bigger, okay? And the way that I think of this one is, well, okay, I had one orbital, that's tiny. Now I have two orbitals, it's a little bigger. I have three orbitals, big surprise, it's even bigger. So 4 orbitals, it's even bigger still. So that's the general pattern. So as you go down in a group, so you got to stay in the same group. The pattern is that the atoms get larger. Why? Because there's more protons and electrons, they need to have more orbitals. All right, so under our keywords and pronunciations, the atomic radius, the average distance between the nuclei of two adjacent atoms of the same kind. Basically, it's a measure of atomic size. That's the main idea. So as you go down a group, there are more orbitals, so the atoms get bigger. Okay, now we're going to talk about within a period. So we're going to talking about going across, and we always go from left to right, just as you read in English. Within a period, however, the size of the atoms decreases from left to right across the periodic table. Keep in mind that within a period, each element has one more proton and one more electron than the element to the left of it, but there's no additional orbitals within a period. The increased positive charge pulls the electrons in tighter towards the nucleus, decreasing the overall size of the atom. Okay, so lithium only has 3 electrons. Beryllium has 4, so you might be thinking, well, it should be bigger. Well, no, it also has 4 protons. It has more protons. Remember before I said think of the nucleus as the mom, okay? Well, now the mom has 4 arms, so the mom's even stronger, and she's going to pull those naughty electron kids close to her, give them a big hug. All right, boron has 5 of each. Well, it's like a mom with 5 arms, and that mom's going to grab those 5 naughty electron kids and pull them even tighter. Well, fluorine's got the naughtiest kids of them all, but it's okay because she has 7 arms. She has 7 protons in the middle, and those 7 protons are going to squeeze those 7 electrons in a big hug and make it smaller and more compact. So that's one way to think about it. All right, great. So let's add that to our notes. So as you go across the period from left to right, there are more protons and electrons. Okay, but because there's no more orbitals, it's not getting bigger. So the same number of orbitals, but the atom gets smaller because the more protons, the more it pulls the electrons towards the nucleus. Again, mom, which of course is the nucleus, the center of it all, with more arms, pulls her naughty electron kids in a bigger hug. So it might sound silly, but sometimes the silly ways help you remember, and if you can remember without the silliness, that's fine. If you need a little bit of silliness to survive chemistry, that is also fine. Missing data. For certain elements on the periodic table, there is no readily available data regarding some of the properties that are shown, especially for the ones that are man-made. Okay. Throughout this lesson, if you click on an element and no data appears, it is not an accident. In other words, they're leaving it blank because, especially with the man-made elements that may only exist for a fraction of a second, they don't have all that information. So, other than that, if you do go in, you can go ahead and click on them just to remind you which element is which, but that's all it shows. Atoms vary in their ionization energy. Okay, let's talk about what ionization energy is first. It's the energy required to remove an electron from an atom. So I want to get rid of this electron. That takes energy. Specifically, that energy is called the ionization energy. This ionization energy of an atom depends on where on the periodic table the element is located. So when energy is absorbed by an electron, it may be enough to ionize the atom or get rid of the electron. And now this atom has less electrons than protons, so it is a what? An ion, but specifically it is a cation. It's positive. So with enough energy, the electron escapes the pull of the atom. The removal of the first electron from an atom is called the first ionization energy. The ion produced as a result of the first ionization energy will have a +1 charge. Because you lost an electron, you have one more proton than electrons, so you have a +1 charge. The second ionization energy is the energy needed to remove a second electron from a +1 ion. The resulting ion will now have a charge of +2. Because you lost 2 electrons, which means you have 2 more protons than electrons, so an overall +2 charge. And you guessed it, the third ionization energy is the energy needed to remove an electron from a +2 ion, and the resulting ion has a charge of +3. A higher ionization energy means it takes more energy to pull an electron away from an atom. You can use the periodic table to predict and compare ionization energies. In general, the first ionization energy increases from left to right across the periodic table and decreases down a group. So you can memorize this stuff, but that's not going to help you long term. You need to really think about the why, and if you can think it through, you will know it for a much longer time because you're not memorizing, you're actually learning it and you're learning the why. So this is an example of when it's important to learn the why. As you look more closely at the ionization energy trends within a group, keep in mind that the size of atoms increases with increasing atomic number within a group. As you can imagine, the larger the atom, the less will be the effect of the pull of the nucleus because the electrons are farther away since they are in more distant orbitals. So the ionization energy is lower as you go down a group. All right, so low energy is the light color, high energy is the dark color. So it's darker, light, lightest. Darker, light, lightest. You can see it takes less energy. Now, if you kind of missed the why, think about the mom example. So this mom has 6 orbitals filled with electrons, or 6 rings of kids running around her. Is she going to be able to grab the kid that's way out there in that farthest ring? No, she can hardly reach that far. That kid can easily run off and get some ice cream. Whereas if you look at lithium, the mom only has 2 orbitals. And so lithium can easily grab that naughty kid that's in the second orbital because they're not that far away. So that's a good way to think of it. Because the electrons are farther from the pull of the positive protons, it's easier to escape. And so we're going to add that to our notes, ionization energy, the amount of energy required to move an electron from an atom. Ionization energy decreases down a group. It's easier to remove and take less energy to remove an electron that is farther from the proton's pull. And so if we look at this, the protons are what's hanging on to the electrons, and here it's really close, so it's got a tight hold on it. Look at how far away this electron is, and so the proton doesn't have as strong of a hold on it because it simply has a greater distance. Just like magnets. When magnets are really close together, they're very attracted to each other. When they're farther apart, there's not as much attraction. So distance does matter. As you move from left to right across the period, the ionization energy increases because with each added proton, the effective pull of the protons in the nucleus increases, holding the electrons closer and increasing the energy needed to remove an electron. The units for ionization energy are electron volts. An electron volt is a measure of a very small amount of energy. So it's the same idea as before, where when you go across, there's more protons. So the neutron is really holding them nice and tight and keeping them there, so it takes more energy. Another way to think about it is this. Ionization energy increases across a period, easiest to remove electrons from group 1A, hardest from 8A. Electrons want a full outer shell. Atoms with 1, 2, or 3 valence outer electrons want to lose electrons, because if I lose this electron, then that orbital is all gone. Now my outer orbital is full. Whereas if you have 5, 6, or 7 valence electrons, they want to gain electrons. They want to say, hey, you know what, give me 1 more electron to get full. I don't want to try and lose 7. That's too much work. So it takes a ton of energy to remove all these electrons. So it's never going to happen. They're going to gain. So it would have a very high ionization energy. So atoms 5, 6, 7 with 5, 6, 7 valence electrons want to gain electrons, so it would take an extraordinary amount of energy to force these atoms to lose electrons, so a high ionization energy. And if they already had 8 valence electrons, like the noble gases in the last column, they're not going to lose it because they're already stable. So that's why the ionization energy increases as you go across. It's harder and harder to remove it because there's more valence electrons. All right, I am going to stop here and we'll pick up with this slide in the next recording.